I would like to acknowledge the Wurundjeri people, who are the traditional custodians of this land. I would also like to pay respect to the elders both past and present of the Kulin Nation, and extend that respect to other Indigenous Australians present.
A little rough at places, especially towards the second half when I talk about the new stuff. But I'm thinking about this as sort of like a dry run for my completion seminar, which hopefully should follow relatively shortly. So in that regard, if there are things that seem, and I address this specifically to the students, and I don't know if they're honest students or anything, but people with less expertise, if something seems unclear or is confusing to you, that's definitely a me problem and not a you problem. So, let me know. You'd be doing me a huge favor if you ask me questions and clarifying things like that. So with that preamble out of the way, let's talk about it. So source memory retrieval is thresholded. I'm making that claim based on evidence from diffusion modeling of continuous outcome tasks. There's a lot there, but I'm going to break it down as we go. So we'll start with source memory. So when we talk about source memory, we're talking about information about the condition under which a memory was formed as a sort of obligatory sort of, this is why you should care example. I know a lot of people in the hub are interested or are nursing burgeoning interests in misinformation, fake news, that kind of thing. Well, obviously you can imagine the source of some news is pretty important in how you perceive that information, how you use that information to inform, I don't know, judgments, behavior, what have you. So clearly quite important. With more specific reference to why source memory is interesting to memory researchers, it gets at this question of how items in memory, how the content in memory becomes associated with contexts. There are decades and decades of research showing that context is quite important in how memory works. And this is a tool we can use to sort of get at that. So to drill down now to be more concrete, memory for content and context have been studied using recognition and source memory tasks. I know this will be probably old hat to a lot of people in the room, but just for the sake of completeness, when I talk about recognition, I'm talking about a task where you're shown a list of words, and then at tests, you have some words which are new, that you haven't seen before, and some words that you actually did see before. And a recognition task asks, was this item studied or not? In contrast, in a source task, you have a bunch of items which were studied in different sources, and you're just asked to discriminate between, or you're asked to say what source an item came from. So I hope that distinction is clear. I bring these two tasks up together because they're often studied in tandem. And because of that, there are a lot of models which seek to explain performance in both tasks at the same time. One of the questions, or one of the things that these models grapple with is the nature of how information is retrieved when doing these tasks. So these models fall generally into three main camps. There are models which say that retrieval works in a continuous fashion. There's a sort of continuous signal or strength. And yeah, we're probing from that directly in a continuous way. And these models have their roots in sort of signal detection theory. You remember the two lumpy boys in a line in the middle, classic. These can be contrasted with threshold models, which say that there's this threshold, there's this line, there's this limit of memory strength that needs to be exceeded in order for anything to be retrieved from memory. And so if memory strength fails to reach that threshold, nothing is retrieved. It's all or none. It's either perfect retrieval or nothing at all. And there is a third class of models which draws upon both of these. So trying to draw upon both of these processes, which says that different retrieval mechanisms are used in different sorts of tasks. So in terms of source and recognition memory, a very influential type of model, a model of this type is the Jonas-Linus dual process model, which says that there are two processes called familiarity and recollection. And familiarity is kind of what I was talking about earlier. It's sort of just continuous signal of how familiar an item is to you, right? Like if you've studied an item, then it will be more familiar than items that were not studied, so that kind of thing. Whereas recollection is really just a very precise, very rich retrieval of the study event. So the entire context of how you came to see something. So if we relate these two processes to the tasks I was talking about earlier, in a recognition task, as I was alluding to, familiarity can help you because familiar items are more likely to be old. But recollection can also help, because if you remember the rich study event, then obviously it was studied. And so in this way, both familiarity and recollection contribute towards successful recognition. In contrast, with a source task, all the items are studied. It's just a matter of which source they came from. And so familiarity will not help you, says the dual process model. And so recollection, which is thought to be this thresholded process, is the only thing driving retrieval in source. And so source should be, is thought to be a pure recollection process, which is thresholded. I hope that all makes sense. So, which brings me to sort of the central question of my thesis, which is just like, asking, is this true? Is source memory actually thresholded? And I think the way I'll frame the rest of my work is just sort of a series of challenges towards this idea of source memory. So with all that said, there's a second part, right? I was using continuous outcome tasks. Well, what am I talking about there? I won't go too much into details here, but in short, traditionally, a lot of the research which has tackled this question has used two-choice tasks. So cases where, say, an item was presented on the left side of the screen or the right side of the screen, maybe sensory modality, so if a word was seen or heard, or maybe if both words were heard, a male voice or a female voice. These are sort of discrete alternatives. Well, for reasons I won't get into, but I will happy to chat about it later. These continuous and threshold models of source memory begin to mimic each other under a variety of circumstances in two-choice data. And so one way that researchers have got around this or have addressed this is to use continuous outcome tasks, in which responses, rather than being discrete, are made on a continuous, often a circular domain. And instead of sort of just a percentage or a proportion of correct responses, you instead get a continuous measure of response precision. There's a few figures to illustrate what I mean there. These sorts of tasks aren't new. They've been used in classical psychophysics since like the 50s, I think. But more recently, in a study of memory, Wilkin and Ma studied visual working memory using a continuous outcome task. This figure here is from one of Philip's papers, my supervisor, in which people are making judgments about the hue of a noisy color patch in the center, and they're clicking on a response circle, which is a color wheel. So there's a continuous measure there. Now, more directly pertinent to my work is this paper by Harlow and Donaldson, where they looked at memory for the location of words. So rather than left side, right side, it's position along the circumference of a circle. And as I said, you get this continuous measurement of precision in terms of the angular error between the response angle and the target angle. So this is a lot richer in terms of what we can say about people's memory. I said before that these models mimic each other in a two-choice task. Well, in a continuous task, Harlow and Donaldson say that these models make very different predictions. So on the left, you have a continuous model, which is just a single sort of gradual wrapped normal distribution. So you can see it sort of projects down to look kind of normal in the blue line there. And in a threshold model, there are two processes. There's the very high precision on the left, and there's no precision, just guesses on the right. And so when you collapse across the two, you get this particular shape of a distribution, sort of a lifted tail and a very narrow peak. So that's sort of the signature of a threshold model according to these guys. And this is what they found. I won't dwell upon this, but just red line is doing better the job than the blue line. Continuous models really struggle to get the tails and the shoulders and the peak of the distribution. I hope that's pretty visually clear. So this brings us to my work. This is kind of where I jump into the picture. In my first study, I asked two questions. The first is, could these guesses, could these tails in the distribution, could they be due to just failure to recognize items? I'll expand upon this later. And the other is, could these tails, rather than reflecting something about memory, Could it instead reflect something about decision-making? Now let's expand upon those. Now with recognition, there's a body of research which has shown multiple times that people don't have source discriminability in two-choice tasks for unrecognized items. I have a little footnote there just to shout out Julian, my colleague, lab mate and friend, who has a cool paper about how these designs, people's choice of designs can influence what they find. I'm sure we'll hear more about that in his upcoming completion talk. But for my purposes, I'm just asking, these responses underneath the dotted line, are they just unrecognized items? Because if that was the case, then rather than reflecting some kind of threshold in source memory per se, it's more just a proportion of items for which source memory just is absent, that retrieval was never really possible because it's not there. Does that make sense? Yep. Cool. So that's our first question. The second question requires a bit more setup, so please bear with me. We're talking about decision-making and modeling response times. So we'll start with a very broad claim, which I think will be easy to stomach, which is that when people are doing a memory task, they're really making decisions based on the information they get from memory. And there's a very, very rich literature on the dynamics of decision-making processes, which makes it somewhat fraught to draw conclusions about the nature and the structure of memory based on their responses in a memory task, given that there's this intervening process which might transform what you see at the level of people's responses. And so there are specific examples of this, one of which comes from Ratcliffe and Starnes, where they looked at the response times of people when they made confidence judgments with a recognition task. The details aren't too important here, but the point is that the conclusions that people made about memory prior to worrying about decision-making were challenged and changed when we considered decision-making and response times. So this is kind of the importance of characterizing decisions. So one very successful and popular model of decision-making is the diffusion decision model, which I'm sure is vaguely familiar to a lot of people. But again, for the sake of completeness, let's just run through it real quick. So returning to a two-choice task for simplicity's sake, imagine there are two outcomes, response A, response B. The diffusion model says that there's this sort of, it characterizes decision-making as a evidence accumulation process in a noisy environment. And what that means is there's this accumulator, this red dot here, and across time, it might move towards one response, like evidence for response A or evidence for response B. This is the noise in the environment. And if we let this process play out, eventually it'll hit one of the lines, right? And in this case, response A is generated. And there's an example of the path it took. There are a few very key parameters which govern how this process plays out. The first is the mean drift rate. And this reflects how, what it means is how the rate at which the red dot moves. And what that reflects is the quality of evidence entering decision-making. In the context of memory, it's the quality of evidence coming from the memory process, right? That's driving your decision. The other parameter is, oh, that's gone a bit funny, is the decision criterion. So that's the amount of evidence you need to reach one of the two. You can think of that as a separation between the two boundaries. Now, one of the cool things about this model is it captures a lot of very interesting phenomena, such as the speed accuracy trade-off. So when you tell people, hey, be quick, they will be quick, but it comes at the cost of accuracy. And the way this model does this or captures this is by squishing these two response boundaries down. And so they need less evidence to make a response, but they're more error prone. Pretty intuitive. The other thing that can vary, so not only can decision criterion vary across trials, so too can drift rate. So this is variability in the quality of evidence going into the decision process. Another neat feature of the model is it draws an explicit link between accuracy and response times. So remembering that drift rate reflects quality of evidence, right? On trials with high drift rate, and that's the leftmost arrow here, responses are more accurate and they're also faster compared to responses with lower drift rate, which are slower and less accurate. So we call this the slow error pattern, that errors are slower than accurate responses. And this has been observed in a variety of tasks where, especially in memory. We see this a lot in memory. So this is a two-choice task, right? I've spoiled the game, haven't I? I spent so long on that animation, I've just ruined it. This is a two-choice task, but I was talking about continuous tasks. The transition from a two-choice diffusion model to a circular diffusion model is, frankly, mathematically quite involved. But visually and conceptually, as you might have seen, it's pretty simple. You replace the decision boundary with the circumference of a circle. And as before, an accumulator starts at the origin, in this case, the middle of the circle. And now we have diffusion in 2 dimensions to a point along the circumference. And the point at which it hits is the response that is generated in this continuous domain. Now, because we're talking about 2 dimensions now, drift is vector valued, which just means it has 2 things. It has a direction represented by the phase angle, that's where it's going, and also a magnitude, the rate at which it's moving, which is similar to what I was talking about earlier with the quality of evidence, right? Now, this model inherits a lot of the properties of the two-choice diffusion model I was talking about, including drift rate variability. In a continuous domain now, you have responses with high drift, which are, as you see, very accurate. There's what this shows is responses with 0 error are more frequent, and they have fast RTs, and you have low drift, which are less accurate, and slow RTs. And what happens if you collapse across these is you see this blue line, which is the overall distribution of a mixture of high and low drift rates. And the key rationale for us, the key motivation is how much does this blue line look like the red line we saw earlier? So before, in the threshold case, in the red line, we were talking about a memory phenomenon. We were talking about a proportion of responses for which retrieval fails. Well, if we can get the blue line to account for that, instead, we're now talking about decision processes, right? So in that case, the distribution of errors need not necessarily reflect something about memory. It could be decisions as well. So in more concrete terms, we compared two models. There were more, but for sake of simplicity, we had a variable precision model, which is this analog of the continuous thing I was talking about earlier, which has this variable drift rate, variable drift norms. And we compared that to a threshold model, which had 2 processes, one with a fixed positive drift and one with 0 drift. So that's no direction, just guessing. So these are the 2 models we're comparing, blue and red. So let's recap. 2 questions. Could guesses be due to recognition failures? And could the heavy tail error distribution be a reflection of decision rather than memory phenomena? So I'll run through the experimental paradigm real quick. It's important that you remember this because I use this again and again and again. So just real quick, there were 4 phases. First, people encoded items. They were shown a location, they were shown a word, and they had to indicate they'd paid attention. If it was outside of a certain range, we got them to do it again until they got it right. Then people had to do just arithmetic distractor task for about 30 seconds. We then asked them to do a recognition task. And this was just done on a 6 points confidence scale, sure, new, sure, old, yep. And then they did the source retrieval task. They replicated what source they think an item came from. Cool. So could source guesses be due to recognition failure? Well, here was the observed distribution of response errors. And here it is broken up by what rating each item got in the recognition task. And what I hope this shows is, yes, the blue area, the unrecognized items are uniform, but it doesn't account for all of the tail. There's still this sort of uniformity, these heavy tails in the red area. If that plot's unclear, here's what I used in the paper of this. And now we're splitting against items recognized with the maximum value, high confidence, with less confidence, and then less than 3, so unrecognized. And what this shows is people are generally pretty good at recognition, right? Like they're responding with very high confidence in most cases. And as I said, items recognized with lower confidence, they look kind of uniform, but it's nowhere near close to explaining the tails. So what that tells us is no, people still seem to guess when we only look at items recognized with high confidence, which brings us on to our second question. What about decisions? What about this drift variability story? I'm sorry if this is a little hard to see. I kind of just copy pasted it, so it's a bit low res. But the red line is the threshold model and the blue line is the variable precision model. And that blue line is struggling. Hey, it's not doing very well in terms of capturing the peakiness of the distribution. And we can zoom out to look at all the other participants in my data set, and you'll see that there's a fair bit of variability. You know, people vary in how they respond. Some people guess more, some people are more precise. But in all these cases, the red line is doing a better job than the blue line, threshold over variable precision. So what's going on? I told you that there's this, I sold you on this variable precision thing. Why isn't it working? Well, to look at that, rather than just consider the sum total or the overall distribution of errors and response times separately, we can look at the relationship between response times across response errors. Now, this next plot needs a bit more setup. I dropped it in my most recent paper, and Adam left a comment saying, you cannot just put this in here without explaining it. So here I am explaining it. This is the distribution of response errors. You've seen it before. It's symmetric, right? It's circular. And we don't really care too much about that. So we can just fold it in half and just look at the absolute distribution of absolute errors. Now what we do is we take the error quantiles. So the 0.1, 0.3, 0.5, and 0.9 in this case. And all that means, not to be patronizing, is items in the red box are the most accurate 10% of responses. This is the next bin, and so on and so forth. And now for each bin, we calculate separately the response time quantiles. So in this case, this red square represents the fastest 10% of the most accurate 10% of responses. Okay. Now we do that for the other response time quantiles and for all of these bins. So what we end up with here, if they're all in a line here, if they're all straight, then we're saying that response times don't really change across error. You know, the response time quantiles remain the same as we move across the bins. But you can imagine a case where, say, less accurate responses are a bit slower, and so these get shifted up. And this is what I was talking about earlier in terms of the slow error pattern. If errors are slower than more accurate responses, this is what you would expect to see, this sort of gradual increase or this gradual shifting up of response time quantiles as we move from left to right. So if hopefully that all makes sense as we move into this next plot, which is the actual data we observe for one participant. And while there's strikingly some movement in that 0.9, the triangles at the top there, it's pretty sharp. The blue line can't quite get the sharpness of that uplift. And for the other time quantiles, the square and the circle, which are kind of one amorphous blob there, I realize. But there's not that sort of gradual bowing up that I was talking about, right? That's not what the variable precision model wants to see. So constrained by this data, it's hard for the continuous variable precision model to account for the joint data. And yeah, again, zooming out, same thing. Variability between participants, but in all cases, red line better than blue line. So to sum up that first study, people don't guess. Yeah, recognitions doesn't explain that. And also diffusion models with a mixture with guesses are preferred. They're doing better than mixture models, diffusion models without. So it seems like it's not a decision phenomena. What we're seeing really is something about memory. Okay, we're all happy with that? Okay, so this moves us on to study 2. So these are just 2 more questions about the threshold model. So, okay, looks like it's thresholded, but what if? First question is, are these findings robust to changes in how we present source? So you might have noticed something a bit funny about my paradigm earlier. It's a memory task in case you forgot. What happened was people were shown a location and then they were shown a word, right? So the item and the source were spatially and temporally disjointed, which is not how we typically think of, context, right? It might be more intuitive to just present a word in a location. So the original reason why we use a sequential process presentation format comes from Harlow and Donaldson. They were afraid of people unitizing item and source. But what we're saying here is, maybe that makes it harder to bind items and sources. Maybe some of that failure to respond in the source task is attributable to just how source is presented. If we really are saying something about the nature of source memory retrieval, it should happen regardless of how we present it. So that's what we're testing here. Again, the second question is a bit more involved, which is, are these guesses actually due to confusions between targets? Let me expand upon that now. So imagine now that you're a participant in my task, unlucky for you. You get shown a bunch of words, right? And you get asked where chord was located. Now, if you're paying attention, you'll know chord was that gold distribution. And so you'll have this like a distribution of responses centered on that. But imagine you got confused, right? You know where words presented, but you get confused between words. Maybe you're asking about a different one. Maybe I'm thinking of a different one. And so you might get these responses in the purple centered on the non-targets instead. So these aren't guesses. You just got confused about what is being probed. So we can increase the number of non-targets in a list as before. And the point I want to make here is on a single trial like this, the distribution of intrusions is very systematic. It's centered on all the non-target items. But because where all these items are uniform, they're just randomly pulled and randomly shown, across many, many trials, these intrusions will start to mimic guesses. So they're uniformly distributed in terms of distance from the target. So given that there's this mimicry, how much of this apparent guessing is actually just due to confusions? I forgot the citation here, but this is work done by Paul Bayes in the visual working memory literature, which looked at this kind of thing, and they found that rates of guesses were previously estimated to be about like 60% without intrusions, but once you included intrusions, it went down to like 14%. So in that case, it was a huge decrease when you considered the possibility of these intrusions. So how can we tease these two apart? Given that they mimic each other, how can we tell what's going on? Well, usually what we're plotting is the distance between a response angle and the target angle, right? Instead, we can plot the distance between the response angle and each of the non-target angles, so each of the non-target items here. So if we plot all of those together, this is what we get in our data set. And what should strike you right away is there's this lump around 0. And what that tells us is that for a proportion of these distances, a proportion of items, the response angles are closer to non-targets than you would expect by chance. So if there was no relationship between where the non-targets were and response angles, the distribution should look flat. It should be a total uniform distribution. So the fact that we see this central tendency is reflective of intrusions. Okay. Now, I come back to this point a few times, and I realize it's a somewhat wordy one. My poor, long-suffering partner, who I ran these slides for last night, got confused about this. So as an act of desperation, I'm just going to put a picture of my cat here. Next time you see my cat, he's very cute. Next time you see my cat, remember this is what I'm talking about. This is the distances of the response angle and each of the non-targets. Okay, that's what the cat means. So our guess is due to intrusions. We compared at first 3 models. The first was a pure guess model, and this is directly analogous to the threshold model I talked about in study 1. There are responses and there are guesses. The next model was a pure intrusion model, which makes a very strong claim that there are no guesses. All errors, other than noise for the target, are just due to confusions. So there's no uniform guessing at all. There's no blue bit. And the third model combines both. So intrusions and guesses both happen. So keep that in mind. So again, we were interested in the presentation format. So we had 2 conditions, 2 presentation conditions, one in which we used in study 1, where items were presented in a disjointed fashion, and another where items were presented simultaneously. The rest of the experiment was exactly the same. So that all holds. Don't worry about this for now. I'll come back to this. So our first question, again, yeah, a bit repetitive. Are these findings robust to presentation format? And no, not really, right? On the left is response errors in a sequential format, and on the right, simultaneous. The peakiness and the heaviness of the tails is the same in both. So it seems like this characteristic shape isn't affected. It's robust to changes in how we present source and item. So great, it doesn't matter. So the more interesting question, what about these confusions, these intrusions? Well, On the left here, we have the distribution of response errors again, and the model fits to them. And what I hope you'll see is the red line's not doing great. That is the pure intrusion model. So that's with no guesses. With no guesses, we struggle to get the peak of the distribution. Let's look at it the other way though. Remember the cat, remember the non-target angles. I wish he'd go away. Both and yeah, he's just always in the way. What I hope you'll see is blue line real good on left, pretty bad on the right? Like there is clearly this contribution of intrusions. There's a central tendency on panel B, but the pure guess model just thinks it's going to be flat, and it's not, right? Red line's doing a great job, but again, it's not doing so good with response outcomes. So only the green line, that is a model with error guesses and intrusions, can simultaneously account for both ways of looking at the data. Okay, so intrusions do seem to happen. Intrusions happen, but seemingly so do guesses. Both are important. Now we can be a little bit cleverer about how we think about intrusions now. And the question I'm really seeking to answer here is, well, ask yourself if intrusions are all equally likely. Most of the models of these sorts of effects, these intrusions, binding errors, swap errors, what have you, they explain them due to confusions between similar items. So items which are higher in similarity should be more likely to be confused with each other. Now, in a task like this, items can be similar in a whole bunch of ways, and I'm just going to highlight a few now. Here's a toy task where you have just a list of 4. Imagine Cove is a target. Well, Pups is temporally similar to Cove because it was presented right after it, right? And Cubs was presented right before. So these are backwards and forwards temporally similar. The direction's important for reasons I'll come back to later, but just, yeah, items which are close in the study list are more temporally similar. They can also be similar in terms of where they're presented on the response circle. So the angles they are associated with, that's the spatial similarity. And these both have to do with how and when targets, words were presented. But words can also be similar in and of themselves, right? They can be similar in terms of their orthography. So Cove and core differ by just a single letter. So maybe you get confused between those, maybe more likely than confusing Cove and Pups. But words can also be similar in terms of their meaning, their semantics. So Cubs and Pups are both cute, so maybe I get confused. So these are all sort of factors which might influence intrusion probability. We'll drill down a bit more in terms of the temporal thing again. So imagine an expanded list. And in this case, core is your target, right? Core is your target. We can talk about temporal similarity in terms of lag. Lag refers to the number of positions in the list an item is away. So card happens right after, so it's got a lag of +1. Mugs is 1 after that, so it's +2. You go backwards as well, there's negative lag. And if we change the target, then the lags relative to that are different. Okay. So remembering all that, let's think about how intrusion probabilities change across lag. The intrusions plus guess model, so that's the basic intrusion model I was showing earlier in green. It says that it shouldn't matter. It says that all intrusions are equally likely. But if we say, well, maybe it's got something to do with temporal similarity, well, then we impose this gradient on the intrusion probabilities. So items with a lag of 1 and -1 are more likely to intrude than items further away, further out. Don't worry about the equation right now. I'll break this down. So I talked about backwards and forwards stuff before. A lot of the work in free recall, serial recall tasks have found sort of this asymmetry. Items which happen after are more likely to interfere than items which came before. And so we build that into our model using this parameter here is tau, which just weights the forwards and backwards. So when lag is positive, it's multiplied by that. Yeah. And the other key parameter is the lambda parameter here, which just defines the rate of decay, the drop off. So how quickly the similarity drops off with distance. Look, I probably didn't need to go into detail there, but I worked hard on this animation. I just really wanted to show it off, so humor me. Same thing with spatial similarity. So there's no direction there. It's just kind of drops off with further distance. And in a spatial temporal model, which I'm about to introduce, we simply multiply the spatial similarity with the temporal similarity to get, both contributing. So, which brings us to our results. Cats in the corner, you know what that means? We're looking at non-target angles. And ignore the lines for now, just look at the gray bars. This plots just the non-target angles with a lag of +1. And so there's a pretty strong peak there, right? The evidence is quite good when we just look at, intrusions are quite likely when we look at items with a lag of 1. And as we move across from left to right here, what I hope is visible for everyone is the bars get a little bit more uniform. This evidence for intrusions kind of gets a bit more diluted as we throw in further lags. And same thing as we go backwards. So these are negative lags. They drop off of distance and they're all kind of lower than the top row. So you get what I described earlier, the sort of drop off that's asymmetric. And if we turn our attention to the lines now, the green dotted line, I don't have a legend, is the basic intrusion model, and it's predicting that it shouldn't change across lags, and that's not really what we see. The spatial temporal and the temporal gradient models are capturing some of that. Yeah, yes. So we were just looking at response errors now then, so I'm going to turn my attention now to the diffusion models. So we're looking at both response errors and response times. And what I hope you'll see is purple line good. Spatial temporal model is doing a better job than the other models. And this panel C is that quantile plot. I hope you remember from earlier, I'm looking at quantiles and bins across error. Now, if you can't really make heads or tails of this right this minute, that's okay. It's not really clear, right? Like we have some hints that the spatial temporal model is doing okay, but it's not very clear cut. And that is kind of the difference between the two experiments I ran. So what I described was a study in which we had quite a few participants, I think 36, who did 3 sessions. And what we think was going on there was, even if there was this effect of spatial temporal similarity, maybe there just weren't enough intrusions, not enough observations per participant to model these effects. And so what we did in experiment 2 was we flipped it. So we had fewer participants and they did more sessions. So we concentrated our power at the level of the individual participant. And just for fun, I've thrown some extra models in here, just to keep you on your toes. Orthographic similarity, we're multiplying that with what we had before, and semantic similarity. I will expand on this later, don't worry. These are just models that we also looked at. Right. I should mention we tried a lot of different combinations. We tried versions in which these factors were added together, versions where they were multiplied, without one, without the other. Yeah, it's too much to get into right now, but yeah, rest assured we were thorough. So these were the results from experiment 2. So right away, you'll see that the orthographic and semantic models are doing pretty poorly there. I won't dwell on this too much. I think it's more interesting to look at the what's happening at the joint level. So again, this is response times across response errors. And now the models are getting pulled apart a bit, right? Especially on the right side of the screen, where these are the less accurate responses. You'll see that the basic intrusion model and the temporal model are overestimating how wrong or how the error for the most erroneous responses. Whereas the spatial temporal model kind of pulls it back closer to the black dot. And the reason why that's happening is remembering that we are gauging response accuracy based on the angle, right? Based on the spatial area. So if more spatially similar, if closer intrusions are more likely to intrude, then those responses will naturally be closer to the target in the first place. And so we're predicting that responses overall will be more accurate when we consider these spatial elements. Yeah, there's more to talk about here, but I won't get too much in the weeds. So just to recap real quick, are our findings robust to changes in presentation format? Yep, it doesn't matter how they're presented. And are guesses actually due to confusions between targets? Well, kind of, some of them, but not all of them, right? Guesses still happen. And moreover, we have the systematic model of where these intrusions or what's causing these intrusions. Oh, that's not what I'm saying there. What I'm saying there is this suggests that previous estimates of how much people are guessing are probably overestimates, that there are these intrusions which are happening that people didn't account for. And yes, there's evidence that spatial temporal similarity influences intrusions, but not so much semantic and orthographic similarity. Now, this last point is pretty surprising, actually. We find most models, existing models of memory, would predict that there's this influence of item similarity. Like semantic similarity, especially, if we cast our minds back to like the DRM paradigm, where people kind of remember lists of semantically related words, you get a strong effect there. But even in words, in lists where there isn't a clear semantic theme, we usually see an effect of semantic similarity in free recall, recognition, and recognition tasks. So it's pretty interesting we saw that. And same thing with the orthographic words, right? Now, one reason we thought this might be is simply because of the words we used. So we didn't select for semantically similar words or orthographically similar words. They were just randomly pulled from a list. And so the chance of two four-letter words having an orthographic similarity of being one distance away is pretty unlikely by chance. And so there weren't a lot of very confusable words like that in the pool. Same thing with semantic words. If you're controlling for the number of letters, which I should have mentioned earlier, now I think about it, but yeah, not a lot of four-letter words have the same close semantic relationships. And so what we're thinking is, look, maybe these things do exert an effect, but between word similarities are just too low. And so in our tasks, the spatial temporal similarity dominates. And so to investigate that, we had a follow-up study, which I think I'm in the middle of asking money for from the hub. So consider this a quick sales pitch. We are manipulating the similarity of the lists themselves. So we have lists where words are semantically similar, where they're orthographically similar, and then unrelated as before. And we're just going to fit the same models and see if we get an effect of semantic and orthographic similarity coming out then. So just designed to be a quick, follow-up to that previous study. But regardless of what we find there, I think it'd be quite interesting. If we find this effect of semantic similarity, then we accord with a lot of the previous literature. If we don't, then that's pretty surprising. It would imply that there's something quite particular about this task and the demands it places on our participants. So just to quickly sum up everything, what does it all mean? Well, overall, we've challenged the threshold model quite a lot. We've looked at recognition, we've looked at how source is presented, we've considered decision-making, we've considered confusions between items. And it seems like Elton John, the threshold model is still standing. So what this means, when we go back to my first couple slides, it's pretty challenging for these purely continuous models. They're just incompatible with our source memory data. It seems like memory is driven by these discrete states in the source memory task. I probably need to think more about that and expand upon that, but we'll talk about that later. And in terms of things we can go, where we can go from here, there are a bunch of projects which I think we wanted to do at some stage of my PhD, but we didn't get time to. So I've just thrown them under here as sort of dot points. One thing which we mentioned in the first year, I think, of my PhD, and we haven't come back to, is elaborating on a model such that drift rates, rather than being freely estimated, actually come from the predictions of a memory model. This is something that Adam did in his 2015 model with Simon, where just global matches are determining drift rate distributions. Doesn't matter too much. That's somewhere we could go, to constrain or provide a neat bridge between the two sides. The other thing is to capture guesses and intrusions in a more disciplined or more sophisticated way using racing processes. I didn't include slides to elaborate on this, but one of the things we found when having a mixture of three components is estimating probabilities between the three components is pretty tricky. When you have two, like memory and guesses, anything that isn't a guess is by default memory. But when we have three, it's not super clear, where that probability mass is being moved around. We tried some different versions where changes in intrusions across trials because of non-target similarity. Thank you. Yeah, you know what? Why don't we save that for later? That's kind of where I'm at and where my project is. And yeah, the general story, I think, is there. But yeah, I'll turn it over now to questions, comments, and feedback. Oh, we got a microphone too. Damn, it's a TED talk or something.
Just checking. Oh, cool. Hi, Jason. Thanks for the presentation. I was just curious if how exactly you compared model fit to the actual empirical distributions.
You know, fantastic.
Just curious
question.
if you had like entropy-based measures, just purely eyeballing.
I wish it was purely eyeballing. I'd be out of here by now. No, we used maximum likelihood estimation. So we took all the yes, that's what we did.
Did you use that sort of the deviance or something from the estimate to in some sort of information criterion, maybe?
Sort of. What we did was we sum up the likelihood. Oh, actually, that's just maximum likelihood estimation. We compared the I think in the first case is the BIC, the Bayesian information criterion, and the second case was the Akaki information criterion. But yeah, we used a fit statistic which penalized model complexity and compared them on that basis. I should have mentioned that earlier. Thank you.
Thanks.
Charles has his hand raised.
Yep.
Yeah, thanks, Jason, for really clear talk. I wanted to ask about the possibility of model mimicry. So just knowing the literature on all of the cases showing that you can make analog models look like discrete models and vice versa and so on. I'm wondering how that would play out in your case. And so as someone who doesn't know the internals of the model, I suppose I was wondering how robust are the results for the continuous model to distributional assumptions? So if you put kind of fat tail distributions inside the models, maybe instead of normal distributions, is there any strategy like that which would allow you to account for the data?
Right. That's a good question. I'm not sure I can answer right this moment. I think in all of the models, yeah, the drift rates were drawn from a normal distribution. No, I don't know what would happen. I'm sure Philip has told me at some point, but I've forgotten. I'm sorry.
Yeah, no problem.
Sorry.
Probably important to note though that the circular diffusion model naturally produces one. So the circular diffusion model just naturally produces a von Mises distribution. So when you have drift rate variability introduced, it can produce some different types of distributions, but it's jointly constrained by the response time distributions. So if the circular diffusion model was probably fit to the response error data on its own, it could probably capture it, but it's the response times that are really constraining how it behaves in this case. So it's predicting a slow error pattern that's just not seen in the data. So we did try with some different distributions and didn't seem to matter too much, but our suspicion is that it's probably not due to distributional assumptions, but instead due to the theoretical properties. So how response times relate to the model and how they change with error.
There he comes to my rescue. I should have taken notes. But yes, I think that's true. It's the response times which are constrained in the model. Oh, yes.
I have probably a somewhat naive question, but
Please.
I was wondering what an example of like a type of memory that would produce sort of a high versus a low drift rate, because I understand the diffusion model in terms of decision making.
Yeah.
I was wondering, you know, what would be an example of a kind of memory that would be kind of easier to retrieve versus harder to retrieve, sort of in that context.
I don't know about type of memory,
but however you, I guess that's what I'm trying to understand.
Yeah,
is the differences there. or source or?
Yeah, I think information memory is stored with varying degrees of precision, right? Like some memory traces are stronger than others. And so when we probe memory, when we draw the information from memory, that is going to vary. And that's what's driving the variability in drift rates. Does that make sense? It's how well that item is represented in memory.
Do you think that there are certain factors that would vary?
Yeah.
What type of factors?
Yes, absolutely. I mean, this kind of thing is studied quite a lot, I think. If I think back to just like how, well, one example is how many times you see an item. So repetitions of items can increase the strength of an item, how long items are shown for, that sort of thing. But yeah, even when items are all similar in how frequently or how long they're shown in our tasks, you do get a bit of variability. And so, yeah.
Thanks.
Thanks.
Awesome. I think that's about time anyways. Thank you, Jason, for a really interesting talk. I'm sure your completion seminar will go great. And thank you everyone for the questions. Just a reminder, we have a little off-cycle talk on Friday at noon. If you want to see Chris Van Heer, who will be talking sort of half, this is your life, half sort of talking about her transition to industry. So Sasha will send out a reminder about that, but keep that in mind. And I think nothing next week. Is that correct, Sasha? Because Chris is sort of taking it up.